Today, what we'll talk about is either reviewing or introducing matrices, depending on whether you've seen it before, it'll be review, or if you haven't seen it before, it'll be introduction. We'll then on Monday look at solving linear systems using matrices. We already looked at solving linear systems using the Laplace transform, but there's another way of doing it, and that's to use matrices. So this is the warm up, as it were, to Monday, where we'll actually go through the whole process of solving a linear system of differential equations using matrix methods. And with that, why don't we jump into announcements? The only one that I have is to please fill out the TVAL if you have not already. Any constructive criticism or positive feedback you have is much appreciated to know what I'm doing right or what could be done better in your opinion. So if you get a chance, please fill that out. And then let's open it up to questions. So what questions do you have that you want to go over before we jump into matrices? All right, there's a request to look at part B, question 2, written homework 7. You can certainly take a look at that. Let me bring it up. Okay. So written homework 7. This would be question 7.2, looking at part B. So if we have our differential equation y double prime minus xy is equal to 0, and just for reference, in case we need it, we have these initial values. Then it says in part B, differentiate both sides of the differential equation with respect to x to generate a new equation. All right, if we do that, we take this, take the derivative with respect to x on both sides. That is, we're just taking this diff EQ and taking the derivative like so. And maybe that's a little hard to distinguish. Of course, on the right-hand side, we'll have 0. But then on the left-hand side, since the derivative is linear, we can distribute it across this this difference, and we end up with the third derivative of y with respect to x. And then we have the derivative with respect to x of xy, like so. Now what we're going to do is use the product rule here. And if we do that, we end up with, let's see, negative y plus x y prime. Actually, let me write that a little neater. We have y minus or plus xy prime. And then we have y triple prime here. If we wanted to rewrite it, we could say that y triple prime is equal to xy prime plus y. Now, the idea is we know what y of 0 is. We know what y prime of 0 is. Part A asks you to substitute in to find y double prime of 0. So we're essentially trying to find more initial value information. So we want y prime or y double prime is 0. Will end up being whatever. Now we're looking at y, maybe put a different color, y triple prime of 0 is equal to whatever. So that's the kind of point of these first few steps, is to generate more initial value information. And in this particular case, you can now substitute in 0, well, x of, when x is 0, this term becomes 0, then you have y of 0, which and then that'll give you y triple prime. And then after that, in part C, it asks you to extend, and what you want to try to do is find, and there's a nice formula to do it. You then want to continue and find also, let's say, the fourth derivative of y evaluated at 0, and the fifth, and so on. But you just kind of follow the same types of steps here. And now notice we don't know exactly what y double prime or y triple. Actually, we know what we don't have formulas, I should say, for y double prime, y triple prime, and so on. But we can at least find out what the initial value information is for those derivatives. So that is that part. Another question was asked, how are the review assignments going to work? And I'm not sure quite what you mean by that. Maybe you could clarify if you mean when are they going to be available or something to that effect. Another question was asked, can you go over problem 1 and 2 on yesterday's online homework? Sure. So that would have been day 34. And let me bring that up. All right, day 34, questions 1 and 2. And let's see. Yeah, these are definitely good to review. So I'm going to do, let's see, are they the same? Let me double check. Are they similar? Yeah, they're similar. So I'll just pick the first one because it's going to work out to be the same either way. So this is day 34. And it's question 1, or a version of it, because we often all get different versions. The one I have says this: take y double prime plus 2xy prime minus 4y is equal to 0. And it gives initial value information, y of 0 is equal to 7, and y prime of 0 is equal to -9. And for those of you who were here yesterday, is the audio much better today, or is it about the same? I using a different mic today, and I'm curious. Okay, good. Cool. For those of you who said something in chat, appreciate it. All right, so this problem here, where we're solving with series solutions. Now, what you could do is actually write a solution like this if you wanted. We won't, but just as a kind of reminder of the possibility here, we could write x minus 2 to the k power, for instance. Or you could do, let's say, x minus pi, if you like. You can center this series about different values. You have flexibility because there's actually no singular points. So each real number you can center this series around. But unless there's a great reason to otherwise, it's usually easiest just to center it around 0. So that's why we end up with this just x to the k. But just a heads up, you can center it around any ordinary point that you want. Now, once you have this set up, or you say, let's suppose this is a solution, and maybe I'll write that. So suppose this is a solution. All that's left to find, and it's not like it's a small thing, there's still quite a bit of work to do, but in principle, what we need is to just find these a sub k's. Once we know these, we'll know everything about the series, because otherwise it's just x to an increasing exponent. And we know it's infinite number of terms. It's a polynomial. The only thing that's really unknown is what these coefficient values are. So we want to find those. And in particular, for this problem, it just asks us to find the first six, A0 through A5. But if we totally wanted to know the series completely, we would want to be able to find every single term. We wouldn't necessarily have to write them. We would just need to be able to determine what each of the terms or each of the coefficients was. Now, in order to do this, we'll substitute this series into the differential equation. But to do that, we need y prime, we need y double prime. We currently only have y, which maybe I'll color to highlight here. But we also need a y prime and a y double prime. But those are actually pretty easy to compute for series. Once you're comfortable with all the notation, y prime is simply going to be k a sub k x to the k minus 1. Because of that first term being constant, taking the derivative, it'll become 0. So we can just start at k is equal to 1. And then a similar thing for y double prime, we have k minus 1, a sub k, x to the k minus 2. And again, the first two terms from the original series will disappear once we differentiate twice. So we'll just start at the second term. From here, what we want is to write, how do we want to do this? Let's put this down here maybe. Actually, just move all this up and over. So now we want to multiply each one of these series by the coefficient here. For y, we just get negative 4y, which is nothing too crazy. It's just multiplying every term in the series by negative 4. So we get negative 4 a sub k, x to the k. Then for the y prime term, we'll multiply that by 2x. That gives us 2x y prime is equal to the series 2k a sub k x to the k, because we have multiplied by x. So we have x k minus 1 plus 1. And then y double prime will just be itself. We don't multiply that by anything. Now, what we like to do is have each one of these with the same form of exponent for x. So we want x to the k. We want them all to have it. Or we want all of them to have x to the k plus 1, or x to the k plus 2, or whatever. So long as they're all the same. It's probably easiest to do x to the k, but it really doesn't matter just so long as they're all the same exponent. The only one that doesn't have x to the k is the second one, or sorry, the second derivative. This one here, this one has x to the k minus 2. So we want to adjust the indices so that what we get is x to the k here. I'm just going to rewrite this part. So what we're going to do is we're going to take k plus 2 here. Basically replace every instance of k with k plus 2. No, not that. Oh, what am I doing here? We had k minus 1, a sub k, x to the k minus 2. Oh, here's the problem. Yeah, I didn't put k is equal to 2 here. And I also did not put k is equal to 1 here. So, right, we want to get x to the k here. And then we'll, since we're going to add 2 to each of these k's, we're then going to subtract 2 here. So now I'm going to modify these. And what we get is k is equal to 0, k plus 2, k plus 1, a to the, or a sub, k plus 2, and then we'll just have k. And now what we have is x to the k in each case. We'll then assemble this into the differential equation, and maybe I'll just copy this. And let me also copy this part. All right. So if we have minus y, 2xy, and then y double prime, that's just our diffie-q. Then what that alternatively gives us is this series, and this one. And this, of course, is all equal to 0. Now, from here, what we want to do is we want to go by the values of k. So first, we'll look everywhere where k is equal to 0. That happens only in the first and the third case. So we put k is equal to 0. We have the series here and here contributing to that because they start at k is equal to 0. And if we combine those terms, when k is equal to 0, we get from the first one up here, what we get is k is 0, so we get 2 times 1, a to the 2, minus, now we're looking at the second term, or the third term series here, minus 4, a to the 0. That's all times x to the 0. Then we get the k is equal to 1 term. And in that case, all of the series will contribute because they all have a k is equal to 1 part. And if we check that out, we get 3 times 2 a to the third plus 2 a to the first minus 4 a to the first. And all that gets multiplied by x to the first. Actually, I could even write it like this. We even have a recurrence relation. Since all the series will have it, all the indices after that, we might as well actually just put it all together. So k is equal to 1. We get this, k plus 2, k plus 1, a k plus 2, etc. That's for k is greater than or equal to 1, which maybe I will move down just ever so slightly. And that's still equal to 0. Then from here, what we do is we say the first term has to be equal to 0. And that gives us a relationship between the two. So we say 2a squared is equal to 4a naught. So, or not a squared, a sub 2 is equal to 2a naught. And in particular, I'm going to jump back that we said that y of 0 is equal to 7. So since y of 0 is equal to 7 and A not is 0. This is 2y of 0. That's the same thing as saying that A2 is 2 times 7, which of course is 14. So we know A naught is 7. We know A2 is 14. We'd like to know A1, for instance. We know that A1 is going to be equal to y prime of 0. And I'm going to jump back because I can't remember what it is. It's -9. And then all of this here gives a what's called recurrence relation. And what that looks like is, let's see, what we get k plus 2 times k plus 1, a sub k plus 2 is equal to 4 minus 2k times a sub k. And that is a sub k plus 2 is equal to 4 minus 2k divided by k plus 2 times k plus 1. And I'll get that gets multiplied by a sub k. So if we want to know what A3 is, that's going to be equal to, and let's see, A sub 1 multiplied by k is 1 in this case. So we get 3 times 2, and then 4 minus 2, which means we get 2/6 or 1/3 times A1, which is -9. So we should get -3. And then it's the same thing for A4 and A5. You just use this formula here. To get A4, we would use A2 by substituting k is equal to 2 into this equation. And then for A5, we would substitute in k is equal to 3 into this equation. Okay, I'm going to jump back to questions that people have. There was another request. Oh, going back to review. Yeah, so thanks for the clarification. What's up with review? Review will be similar to how it's been before. So maybe I'll put this in the announcements part. So review for the quote unquote final, or another way to think of it is exam 4, because it'll be very similar to the others. Exam 4 will be cumulative. It'll be roughly the same length, same difficulty, roughly from before. The reviews for it will take place on Tuesday, Wednesday, and Thursday. Tuesday will be review for, higher order. Wednesday will be Laplace, in theory. That's what those days are, though you may work ahead. And then Thursday is going to be series. Now, I think it was helpful. You can tell me if it wasn't helpful or if you want in chat, but I can only imagine it was helpful, at least for some people, to have them available early. So maybe what I'll actually do is even now, and by now I mean, after we're done here, to have them be available essentially right away. So I'll make available sometime today. That is for all of them. There's no first order. And my thinking there was, one, we'd want to be able to fit in the material on systems. And actually, I should go back and say series matrix methods. But yeah, since we've done first order several times, my thinking was probably you've got that down pretty well. and the exams seem to suggest that. So these are ones that we've seen a little less. And in particular, series matrix methods will be new for the review, but they'll be, again, the same rough length and so on, and available at some point today. I'll try to get to it right after we're done in class here. And I think that's what I have for reviews. Yeah, that's what I've got for reviews. So other questions that people had, I see one or two in here. Let me, and actually, while I'm at it, since we're at announcements, another question I saw quick was, will participation and attendance points be put into Canvas before the final exam? Yeah, my plan is to input attendance and participation. That'll be put into the gradebook at least by Wednesday of next week, which will be before the exam. Probably more like I don't know, towards Monday or maybe even this weekend, just depending on how things go. Will definitely be posted before the final exam, just so you have a chance to check it out. Yeah, probably I'll even do it today, just so you have a sense of where you're at with everything, so you can kind of mentally plan for the last exam. All right, other questions people had. Someone asked to go over question 4 from yesterday's online homework. Sure, so let's look at that. And actually, before we get a chance to get to that, another question on kind of general things here. Will I change the grades of our test with the rule from before? Yeah, I think the rule I said was, wait, what did I say? Oh yeah, the first exam, the lowest exam score will be replaced by the highest. Yeah, I'm actually, for the person who reminded me of this, thank you. I'm glad you did. I will also change that today because all the 3 exams are in. So there's actually a few things that should change at some point today, namely the availability for the reviews should open up. I'll try to get to it after class today. I'll post the attendance and participation today since I'm kind of doing this all at once. And then I'll also do the replacement of lowest exam score being replaced with the highest. Yeah, so you should see that all change soon, and then you'll, I think, have a good idea about how you need to do for the final to get whatever grade that you're hoping to achieve. Okay, now let's look at question 4 from the homework yesterday. And that question is saying, if we can't essentially use the methods we did for question 1, is there another way to find a solution? So this would be written, or not written homework, but day 34 online homework. And this is question 4. That question gives us something like this: x squared y double prime plus xy prime minus 9y is equal to 0. So there's only a single singular point. In general, there can be more than one, but there's a unique one here. That's x naught is equal to 0. y is at a singular point, because if you substitute it into this coefficient function, you'll get 0. And we care about this coefficient function in particular because it's the one that's in front of the highest order term here. If you go ahead and then center a series about x naught is equal to 0, if we take y to be equal to, I'm going to switch to n, but there's no difference between k. Let's see, x to the n. So this is like x minus 0 or x minus x naught to the n. And now if you go through the process like we went before, so the same thing we just did, what you'll find is that we get all the coefficients being equal to 0. We get that a naught is equal to 0. We get that a1 is equal to 0, and so on, so that a to the, or a sub n is equal to 0. And if all these coefficients are equal to 0, then that must mean, so from this, it must follow that this is equal to 0. And if, okay, that makes sense. I mean, if y is equal to 0, you take the derivative, that's 0, that's 0 again when you take the second derivative. So 0 is equal to 0, that works. This is the trivial solution, which often is a solution. It's also a, not to be confused with the singular point, this is a singular solution, which is different than a singular point. So just a heads up that these are different things. But now what we'd like to do is get something that's different than just the trivial solution, something more, because that's kind of, it's not very useful. And what's suggested is that there's another solution of this form, which is y of x is equal to x to the r. And you're asked to try to determine what r is. If we now use this form, just like we did with the series solution, we just want to substitute it in and see if we can, find the information that we need. If we take y prime of x, and maybe for a second we suppose that r is not equal to 0 and it's not equal to 1. In any other case, if we take y prime, we're going to get r times x to the r minus 1. And then if we take y double prime, what we get is y double prime is r minus 1, x to the r minus 1. Now substitute all these in. We get x squared y double prime plus x y prime minus 9, y is equal to 0. Or substituting in, we get r minus 1, x to the r. I think I wasn't clear that that was negative. Now it's x to the r. Why? Because we have x to the r minus 2 and then times x squared. So we have x to the r minus 2 plus 2. Then we have plus x r. Actually, we get just r x to the r. And then minus 9 x to the r is equal to 0. Of course, we can then factor out the x to the r, leaving us with r squared minus r plus r minus 9. And that, of course, even simplifies a little bit so that what we get is r minus 3 and r plus 3. Now, it's not going to be the case that x is always 0. So supposing for some x values that are not 0, that must mean that this has to be 0. So it must be the case that either r is equal to 3 or that r is equal to -3. So this process is a little bit simpler than, actually quite a bit simpler than using the series notation. But we switched to this because we weren't able to center it around 0 here because 0 was a singular point. It was a singular point because substituting 0, this thing, into this coefficient function gave us 0. So that's what caused us to switch over to this. Okay, that's that question. And I think why don't we get to matrices, just so that we can make sure we cover that material. And I'm assuming it'll either be familiar or relatively easy to pick up. So I was very happy to go through these questions. Hopefully it helped you understand the series material better. But now let's look at matrix addition and multiplication. Matrix addition, actually, maybe I should even start with what a matrix is really quick, just to be clear. So a matrix is an array of numbers, such as 2, 1, 1, 0, but you could also have something like this: 3, 1, -1, 1, 2, 0, like this. You could have something like so. You could have something like this. Lots of different things you can have. In general, what you have is a number of rows and a number of columns. In this case, we have 2 rows, 2 columns. And just to make it really clear, let's say we do the rows like this. So that's where we get the rows from. And then the columns, those look like just so. So when I say rows and columns, what I'm talking about is like this, like what you'd expect. So we have 2 columns here. We have 1, 2, 3, 4, 5 columns here. We have 4 columns here. We have 3 rows here. We have 1 row here, and we have 4 rows here. We would call this a 3 by 2, a 1 by 5, and a 4 by 4. So it's always number of rows times number of columns, or not times, but I guess by rows by columns. This is what's called the dimensions of the matrix. Now you can add, subtract, multiply matrices as long as they have the right dimensions. You can add matrices if they have exactly the same dimensions. For instance, you can take the matrix 2, 1, -1, 0, and you can add that to -3, -3, 4, 1, because they have the same dimensions. They're both 2 by 2s. And how you add them is simply, you're going to take and add them component wise. So you take this component here and you add it to this component. That would give you, of course, -1. Then you would take, always component wise, say this component, add it to this component, and that gives you -2. Filling in the last couple in the same way, I think we'd get -3 and we get 1. Notice that you also end up with a matrix of the same size, kind of, which might be obvious why. So this is matrix addition. You cannot add matrices of different sizes. As an example, you cannot add, say, 2, 1, negative 1, 0 to, let's say, 3, 2. That's not defined. And in some ways, it's kind of obvious why it's not defined. Yes, it's true that you can match up some of the coefficients. Like you could say, in theory, this is the first row, first column entry, and so is this. All right, that's fine. But then you're going to have a mismatch when you look at this one. Okay. So you're not going to be able to decide what you should add here. So you need to have the exact same dimensions. Positive 3. Good catch. Thank you. So you're not going to be able to, yeah, thank you for the catch back here. It should have been positive 3. So you're not going to be able to decide what this sum should be because you're adding 1 to what? So you need the same dimensions, exactly the same, so that you can always match up entry by entry. With matrix multiplication, it's in some sense a little more forgiving because you don't need both of the dimensions to match up exactly. What you need is what we call the inner dimensions to match up. And I'll say more what I mean by inner dimensions. So if you have a matrix that's, let's say, we'll call it A, and it's m by n, we multiply it by b, what we need is for b to be n by something. We don't actually care what this m and the p are. What we need is for these two to be the same. So we need this n and this n. We need it to be the same number, which maybe I'll color here. What you'll end up with once you do that is a matrix that's m by p. So if we, let's say, color p to be, say, green, we color m to be, I don't know, let's say, seems like a yellow to me. Then we get this here. So the inner dimensions we need to be able to multiply. And then what we end up with is, in some sense, the inner dimensions canceling and leaving us with the outer dimensions. All right, now let's look at how this works. This can be a little more confusing. And even if you've seen this before, it could be potentially easy to forget. Let's say we have, actually, let's do a 2 by 3 and then a 3 by 2. And let's say here we have 1, 2, 3, -1, -1, 0. And here is 4, -1, 2, 1, 1, 5. Now, how we multiply this, just like how we determine the dimensions, it's always row, column. From the first part, we take a row. From the second, or from the first part, I should say, from the first matrix on the left, we take a row. From the matrix on the right, or the second matrix, we take a column. And let's see, how do I want to color this? So we're going to take a row, say like this, and then take a column, say like this. Now this is the first row, first column. So that will give us the first row, first column entry of the resulting matrix. Now we said, here's a 2 by 3. And then here's a 3 by 2. So what we should end up with is a 2 by 2. We end up with the outer dimensions. Now, when we match these up, this row and this column, what this should look like is taking, say, these entries, 4, 2, 1 from the column, and then multiplying them by the entries 1, 2, 3, and we multiply matching entries, and then we add them up. If we do that, I think we're going to get, see, 4 plus 3, which is going to be 11. So this entry is 11 here. Then correspondingly, if we take, say, the first row, second column, so this would be, just to be clear, this is the first row, first column. And when I say first row, I mean the first row of the first matrix, which is in orange here, and the first column of the second matrix, which is in purple here. If we then take the first row, second column, that's the first row being 1, 2, 3. The second column, which is negative 1, 1, 5. We add all that up. What we get is negative 1 plus 2 is 1 plus 15. So that's 16. We get 16 here. And so on from there. To be really clear, this is the first row. The second row, first column is second row, first column here. And if we multiply those, we'll get negative 4 minus 2. That's it. So negative 6. And then we'll get 1 minus 1 plus 0. So we get 0. Okay, that's how that works. Now, other important properties of matrices for square matrices are the trace and the determinant. And jumping to the next page, the trace and the determinant. For any n by n matrix, you have a trace and determinant. If you've got a n by n matrix, just in general, for n being any positive integer, and it looks like A11, A12, and so on, up to A1n, then A21, A22, and so on up to A2n. If this is going to be our, let's say A, which is an n by n matrix, the trace of A, sometimes or usually denoted TR of A, is going to be equal to just the sum of these entries. So I'll put I here. I is equal to 1, and it goes up to n, which another way to write this is A11 plus A22 plus dot, 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 up to ANN. So the trace, let's see, how do I want to color this? Let's say it's this magenta. And then what I'll do is I'll take the diagonal here and I'll color it like this. So the trace is just adding up all the main diagonal entries, where the main diagonal is this here. The determinant is not quite so easy. What one actually wants to know is the determinant of a 2 by 2, and then you build it up from there. So you get the determinant of a 3 by 3 by reducing it down to 2 by 2s, the determinant of a 4 by 4 by reducing it down to 3 by 3s, and then down to 2 by 2s, and so on. So you're ultimately always reducing down to 2 by 2s. We say that the determinant of a 2 by 2 matrix, say A, B, C, D, is going to be equal to A times D minus B times C. Then finding the determinant of a 3 by 3, if you have, let's say, A, B, C, D, E, F, G, H, I. Actually, just for the sake of not making it more complicated than it needs to be at the moment, I'll just say the determinant of a 3 by 3 is computed using determinants of 2 by 2 minor matrices, so-called. And when I say minor matrices, I mean like smaller matrices within the 3 by 3 matrix. And the question is, well, what if it's not square? If it's not square, then there is no trace and there is no determinant to compute. The only time you'll compute it is for square matrices. Now, in addition to finding the trace and determinant, there are some really important characteristics of a matrix, namely its eigenvalues and then correspondingly eigenvectors. We don't need to go into why they're so important, but if you come across a linear algebra class, you'll talk extensively about why they're important and what they mean, what they can tell you about a matrix. But for now, we just need to know how to compute them, and then we'll use that to solve differential equations. Actually, yeah, let's maybe compute a few examples really quick, just to make sure trace and determinant aren't too abstract. If we have, and here you guys can jump in and kind of just test, see if you're getting this or not. If I have this matrix, I'll call it A sub 1. I have this matrix, A sub 2. And if you haven't guessed already, I'm going to ask you the trace and determinant of these. And I don't expect the trace to be very hard. I just want to give you a chance to actually think through it for a second. So if we look at these three matrices, if you would in chat, just so I kind of see where you're at, and if you're not sure, that's okay, but just let me know. I don't know. What do you think the trace and the determinant are in each case? So the trace and determinant for the first one, trace and determinant for the second one. And I didn't say what the determinant was for the 3 by 3, but you may have seen it before. And I claim it's actually relatively easy to compute based on how I've chosen these zeros here. So if you happen to know the determinant of the third one, great. But if not, that's okay. Say, yeah, if you just put in chat what you think the trace and determinant are for the first one, the second one, the third one. If you're not sure on them, you can just say not sure, but just to get a sense of where everyone's at. Yeah, and the trace is just the same as the example. So we're just adding up the main diagonal entries in each case. Okay, for those of you who put something in chat, appreciated. So now you have a record to compare to and see if you got what they are here. So thank you for those of you who put something in chat. If we add up the diagonals, we do the traces first. In the first one, we're just adding 2 plus 1. So the trace in that case is going to be 3. In the second case, 2 plus 5 is going to be 7. And then in the third case, we have 3 plus 1 plus 3, that's 7 again. The determinant for the first one is going to be 2 times 1 and then minus 0 times 1. So we have 2 times 1 minus 0 times 1. That's, of course, going to be equal to 2. In the second case, we have 2 times 5 minus 1 times 1. That's going to, of course, be equal to 9. And then finally, if you happen to know the trace formula for a 3 by 3, what that is going to amount to is the same thing as the determinant 3, 0, negative 1, 3. Do I believe that? Yeah, I believe that. Oh, which also happens to be 9. Kind of interesting. All right. So here are traces, and here are our determinants. Now, in particular, the trace and determinant are going to be really nice for the case of a 2 by 2 matrix. I mean, it's true for any square matrix when you're looking at differential equations, but it's particularly nice for the 2 by 2 matrices for this case. All right, let's go ahead and check it out. So what are eigenvalues? Actually, finding inverse of a matrix. No, we don't need to worry about that right now. Rather, let's find eigenvalues and eigenvectors. So how do we do this? Well, first let's figure out what an eigenvalue or eigenvector is. So let AN be a square matrix. And let's say it has real entries. You can have complex entries for matrices, which is pretty cool. But let's just say it's real entries. So we say that if you can take, and actually let's even before that, real number entries, and let's say V with this little arrow over it be a n by 1 matrix, which you can also call a vector. If you have just a row or just a column, we'll often call that a vector. It's like a special case of a matrix. If you have A times V, you multiply this together, you'll get an n by n matrix times an n by 1 matrix. And of course, we know that is a n by 1 matrix because we match the middle dimensions, and then what we're left with after that is the outside dimensions. So that gives us n by 1. If what we get is just V back, with the exception that V is multiplied by a given value, let's say a real number, then we would say lambda is an eigenvalue and V is an eigenvector. So if this is true for some non-zero vector V and real number lambda, then we call lambda an eigenvalue and V an eigenvector. So we have an eigenvalue. That would be, let's say this. And then we have V is the eigenvector. Okay. So let's see. Can we come up with these? We can, but let's see if I can think of a simple example really quick. What we want to keep in mind is this formula. A V is equal to lambda times V. For instance, what happens if we have this matrix 1, 2, 1, 0. And what happens if we take the vector v to be 1, 1? Okay, my question to you, if you multiply a times v, what will you get? So this will help me determine if you're feeling comfortable with matrix multiplication or not. So if you get a times v, I'll claim that you get another vector. What vector will you get? You can just put it as first entry, second entry, as like a list if you want. So if you want to write in chat, you think it's like 3, 7, like this, you can write it as like 3, 7, like that, or however you want. So if you multiply the 2 by 2 matrix here and the 2 by 1 matrix, you'll get another 2 by 1 matrix. Gives you another vector, as it were, which is just a column matrix. So what do you think it is? Or if you're not sure, you can also just type not sure. That's fine. Okay, so for those of you who put something in chat, either way, appreciated. You will end up with a the vector being 2, 2. So you take this column or this row times this column, and if you take 1, 1 times 1, 1, you get 1 times 1 is 1 plus 1 times 1 is 1, so you get 2. Then you take this row times this column, and you get 0 times 1 is 0 plus 2 times 1 is 2. And now notice that we can rewrite this as 2 times 1, 1. That means that since we can just see the original vector as just a multiple, that means that 1, 1 is an eigenvector of the matrix A, and 2 is an eigenvalue. So 2 in this case is our eigenvalue. And then our eigenvector is this here. So eigenvalue. And eigen is something like characteristic in German. It just means like a characteristic value, characteristic vector, particular value and vector. It tells you a lot about the matrix. That's why it's a characteristic or eigen. It characterizes the matrix, if you will. Correspondingly, if we take, let's say, V, or actually maybe instead of V, we'll call it W. And that is, I don't know, 1, 0. If you take AW and you multiply that out, you'll get, I think, 1, 0 back. And now notice this is just W. It's 1 times W. So again, what we have is a eigenvector and an eigenvalue. If I take the same example, and now I'm going to show something that's not an eigenvalue or eigenvector, just to compare. If we, let's say, look at, let's see, U, and we say, let this be 3, 1, for instance. What we'll get when we multiply the two is, let's see, 3, 1, 4, 2. So this is 4, 2. This is not, let me really stress, this is not equal to any scalar multiple times 3, 1. So that shows you that 3, 1 is not an eigenvector of the matrix. And someone asked a question, what type of differential equations can we solve with these? Linear constant coefficient diffeeqs of the form that we saw earlier. So for instance, actually, let me just jump to a new page. So diffeeqs. We'll solve with matrices. They'll look like this. What we'll do is we'll essentially construct a matrix from these entries. We have an A, B, C, D. We'll construct a matrix A, B, C, D using the coefficients. Then we'll look for eigenvalues and eigenvectors. And then once we have that information, we'll assemble it to get a solution. And in the last minute, let me say one more quick thing about the trace and determinant and how it relates to eigenvalues, eigenvectors, at least a little bit. And that's the following. Actually, I can put it on the same page. There's a really nice fact that the trace of a matrix A, I'm going to call this something else for the moment. Trace of a matrix A is equal to the sum of all the eigenvalues. And this is a formula that works even if you have an n by n matrix. Correspondingly, the determinant of a matrix A is the product of all the eigenvalues. So if you want to find the eigenvalues of a matrix, there's various ways to do it, but one way is just to compute the trace and the determinant. And if you have only 2 eigenvalues and 2 eigenvectors, or you have a 2 by 2 matrix, since you have 2 equations, trace and determinant, if you only have 2 unknowns, lambda 1, lambda 2, then you can solve for lambda 1 and lambda 2. 2 equations, 2 unknowns. So it's really handy in the 2 by 2 case. Still useful otherwise, but particularly handy in the 2 by 2 case. Okay, with that, I hope you guys have a good rest of the day. I'll be here for a little while if you want to stick around, but otherwise, take care.
To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.